and has over 20 years of research experience in material science, nanomaterials, thin film synthesis, additive manufacturing, and physicochemical characterization. He has authored more than 90 peer-reviewed publications, hold 10 patents. He has presented at over 85 national and international conferences and delivered more than 50 invited talks. Currently, he is associated with the materials for additive manufacturing at CIMIT, and he is actively involved as an investigator in a multiple research projects. We are honored to have him with us today. Without further any formalities, I requested Dr. Manish Kumar Sinde sir to take over the session. Over to you, sir. Hello.
Thank you. Hello.
Yes, sir. Yeah.
Am I audible?
Yes, sir. You are audible.
Okay. Thank you very much, Pradeep sir, for the nice invitation. And I would also like to thank my friend Aire sir for this invitation. And I am very happy to interact with the students of LVH College as we have a very long interaction and collaboration over last, I think, around 6 years or so. So I'm very happy to be here. I'll start my presentation. Are the slides visible?
Yes, sir. Visible, sir. Proceed, sir.
Okay. Okay, now. Yeah. So today I'm going to discuss about the electron microscopy techniques, which include two very important techniques, that is scanning electron microscopy and transmission electron microscopy. I think Dr. Sudhir Arbuz might have given you the introduction about CMET. So I'll skip this.
Yes, sir. Yeah.
So this is the plan of my presentation. I'll compare the various microscopy techniques, sources of probes, because sources of probe means from where the electron beam is generating. That is very important. Then how the beam interacts with the sample. So beam specimen interaction is also very important. Then I'll discuss further details of scanning electron microscopy and transmission electron microscopy with respect to their basic features, their different modes of operation, typical examples, and sample preparation. So this is not going to be a very fundamental kind of discussion. It will be more on the practical aspects, because as you are now doing your PhDs, you will face a lot of practical problems while preparing samples, while analyzing samples. So I'm going to cover that part more as compared to the fundamental aspects, because that is more important for you. Fundamental information can be obtained from internet. I'll cover some of it, but I'll not go into the details of that. I'll try to focus more on how we can interpret the images, how we can analyze the images, how we can interpret the data, other data that we obtain from these techniques. Okay. And if time permits, I'll show you how we can use a software called ImageJ for analyzing the samples. So when we compare light microscopy with electron microscopy, the obvious question that comes is why we are going towards electron microscopy. We are using light microscopes since our 10th or 12th standard. We are getting good results with respect to the morphologies, and we can see certain small structures using light microscopes. Then why should we go for the electron microscopes? That is the first question that will come to our mind. First thing is, light microscope and electron microscopes, they are similar to each other in terms of their operations. Okay. But certain things are very different. If I give you an example, if you consider a light microscope, it has got an illumination source, that is a light. Okay. Then there is a condenser lens. Then you put your sample specimen. then there is an objective lens, a projection lens is there, and image is formed on the eye or on the computer screen. Okay. So this is how a typical light microscope looks. Okay. Now these lenses, condenser lens, objective lens, projection lens, they are basically used to focus the electron beam and defocus it so that you get the magnified image. Got it? Now, if you consider the transmission electron microscope, it is the exact replica of this light microscope. You can see here, there is an illumination source here also, but here it was the light source having wavelength in the range of 400 to 800 nanometer. But in case of TEM, we'll use an electron beam. Okay, its wavelength will be different. We'll see that in the subsequent slides. Then there is a condenser lens. Then you have to put your sample, the specimen. There is an objective lens, projection lens, and then the image is formed on the fluorescent screen because you cannot. It's not good to view an electron beam directly through the eyes. Okay, so it is the same. Only the fact means the optics is same. The fact is the way the electron behaves is different than the light. The way the light behaves with the sample. If you consider scanning electron microscope, its construction is little bit different, but more or less the same. There is a condenser lens one. There is a condenser lens here also in these two cases. There is another condenser lens two, then objective lens, and then the specimen. That means the specimen is at the bottom. Okay. So the final beam falls on the sample and then we get the magnified image. Okay, so there is a slight difference between the SEM and TEM, but they are analogous to the light microscope, especially the TEM. TEM is highly analogous to the light microscope. Then if they are same, then why we are going towards TEM instead of light microscope? The answer lies in its resolution. The resolution of these electron microscopes is way better than the light microscope. So that's why we are shifting towards the electron microscopes. Because of that greater resolution, you get good quality images. You can analyze your data in a much better way. You can magnify your sample much higher than the light microscope magnification. If you look at the light microscope magnification, it can go up to maybe 10,000 if you have got a very good quality light microscope, but not more than that. Even that at that 10,000 magnification also getting a good quality image is very difficult. The common light microscopes that are available in our labs, they can go up to few hundred of magnifications. Okay, but if you go to the TEM, it can go up to the magnifications of tens of lakhs. Okay, so magnification capacity जी आहे ती खूप वाढली आहे light microscope, electron microscopes मध्ये. Okay. Secondly, the optic system. Here, the lenses that you are using, they are basically glasses. काचेची lenses असतात. They have got some aberrations also, chromatic aberrations and other things. Here, the lenses that are used are basically the magnets, electromagnets. Why? Because electron is an electromagnetic beam. So it can interact with the electromagnetic field and then it can get focused and defocused easily. So here, instead of using the glass lenses, we are using electromagnets as the lens system. Okay. So because of that, again, you get good quality images because that interaction of interaction of the beam with the electromagnet can be controlled by varying the electromagnetic field of that lens. Okay. In glass lenses, you don't have that choice. You have a particular focal length lens with which you have to work. Okay. So that is another advantage of this kind of electron microscopes. So that is why in light microscopes, if you want to choose a different magnification, you have to change your lens because particular lens has got a particular focal length. But here you don't have to change the lens, you just have to change the electromagnetic field. So that is another advantage of electron microscope. Okay. So as I told you, as compared to the light microscopes, the resolution of electron microscopes is very good. So because of that, you get very good quality images. And why it is so? Because of the wavelength. The wavelength of the light microscope is 400 to 800 nanometer, right? In general, if the wavelength is shorter, you get better resolution. It is based on this formula. So the numerical aperture of the lens system depends on the wavelength. Okay. The smaller the wavelength, the smaller the numerical aperture, and you get better resolution. Okay. For example, if you consider light microscopes, they can go up to 500x to 1500x magnification. That means they can magnify the object from 500 to 1500 times. Resolution of such microscopes is around 0.2 micron. 0.2 micron is around 200 nanometer. That means if you have got two objects of 200 nanometer size separated apart, you can clearly resolve them. But if you have got less than 200 nanometer size objects, then you will not be able to resolve them properly. Okay. And this limit was already reached by 1930s. Okay. So if you use this formula, you will get this value, resolution value. So that's why people started to look into other sources of radiation with which they can magnify this, which they can overcome this resolution limit. And then in late 1930s, the electron microscopes were developed. Okay, so the first electron microscope was developed in 1938. Okay. Now, if you look at the electron microscope, the wavelength lambda, which is useful in this formula, here also if you look at this formula, this numerical aperture size depends on the lambda. Okay, the smaller the d, the better the resolution, and it depends on lambda. Okay, so for light, that range is fixed 400 to 800 nanometer. And if you consider the smallest wavelength, that is 400, you get 0.2 micron resolution. Okay, but practically it's sometimes difficult to use that 400 nanometer. But in electron microscope, this lambda or wavelength depends on this formula, h upon square root of 2 mqv, where m is the mass of the electron, q is the charge on the electron, and v is the applied potential difference to accelerate the electrons. So h is constant, Planck's constant, m is constant for electrons, q is constant for electrons. Consider that they are not moving relativistically, then m and q you can consider constant. Then lambda depends on which factor? It depends on the square root of V, applied voltage, applied potential. Okay. So based on this formula, if you consider for TEM, the typical wavelength of an electron, the typical voltage applied is around 200 kV. Now, if you consider this 200 kV and put it in this formula, the lambda that you obtain will be, as V is very high, lambda will be very small. The smaller the lambda, the smaller the numerical aperture, the better the resolution. Okay. Since V is 200 kV, the wavelength, the lambda that you will get will be 0.0025079 nanometer. It is too small, very small value. With that, you will get very high resolution as compared to the optical microscope. In optical microscope, the lambda was 400 nanometer. Here it is 0.00250 nanometer. That means it is at least 1 lakh times higher than the 1 lakh times smaller than the optical microscope wavelength. That is why the resolution is better. For SEM, if you consider, typical voltage that is applied in SEM is 20 kV, 10 times smaller than this. Okay. And then that wavelength is around 0.008588 nanometer. Okay. Which is again very, very small as compared to the light microscope wavelength. That is why you get very good resolutions in SEM and TM. Especially you get even better resolution in SEM, one order better resolution in TM as compared to the SEM because of this wavelength difference. Typical voltage applied in TM is around 200 kV and in SEM it is around 20 kV. So that changes the resolution. Second important factor in any electron microscope is the electron source. The electron source, which generates the electron beam. Like the light microscope generates the light beam. Okay. So when you consider any electron microscope, there are two types of electron sources. One is thermionic emission based electron sources, and one is field emission based electron sources. Based on that, the electron microscopes are also called as SEM or TEM for thermionic emission based sources, and FESM or FETM for field emission based electron sources. Okay. Now that field emission is a separate phenomena. It is the quantum mechanical phenomena where in thermionic emission, you apply very high current to generate the electron beam. You apply very high current to a material, for example, say copper or any other material. Then you get very high beam of electron, or you can apply a very high current to tungsten or lanthanum boride, hexaboride. Then you get a beam of electrons. Okay. But here in field emission, you don't apply very high current, you apply very high potential difference. Because of that potential difference also, a current is generated. That current basically is very narrow beam. Here in thermionic emission, what happens is because you are applying very high current, heat obviously is produced. आपल्या घरचे जे इलेक्ट्रिकल हिटर्स आहेत त्याच्यात काय करतो खूप हाय करंट पास करतो एखाद्या कॉईल थ्रू त्याच्यामुळे काय होतं तो कॉईल हिट होतो आणि त्याचं टेम्परेचर जनरेट होतं घरचे जे हिटर असतील किंवा इस्त्री असेल आयरनिंग प्रेस जी असते ज्याने आपण कपडे इस्त्री करतो तिथे आपण बेसिकली हाच फेनॉमेना वापरतो की आपण व्हेरी हाय करंट अप्लाय करतो बट इन फील्ड एमिशन यू डोंट अप्लाय व्हेरी हाय करंट यू अप्लाय व्हेरी हाय पोटेन्शियल that also generate electrons. Okay, but here what happens because of the very high current in thermionic emission, the temperature of the system rises, and because of that, what happens is the electron beam will also get destabilized, and you get a very broad beam. But in field emission, what happens is you get a very narrow beam. Because of that narrow beam, your resolution improves even further. You get very good quality images. Okay. आता काही पॅरामीटर्स आहेत ज्या मी इथे डिस्कस करतो. For example, the cathode radius, the beam radius, cathode radius is around 60,000 nanometer here in thermionic emission, 10,000 to 60,000 nanometer. In field emission, if you look at here, it is 100 to 1,000 nanometer. So there is a tremendous change in the cathode radius. Because of that, what happens is the effective source radius, the beam radius also reduces. Here it is around 15,000 to 5,000 nanometer, means 5 micron to 15 micron beam radius is there, source radius is there, which means there is a very big beam that is falling on the sample. That reduces again the resolution. In field emission, the beam size is 2.5 nanometer to 15 nanometer. So beam size is reduced 1,000 times. That means your resolution will improve 1,000 times automatically. Okay. Current density also. Current density here is very small. It is 3 to 30 ampere per centimeter square. Because of that low current density, what happens is you don't get very good signal. Okay. Here, if you look at the current density is 5,300 to 17,000 ampere per centimeter square. Because of that very high current density, you get very good quality signal, which is required for the imaging. Okay. So one more advantage of this is the life. Typical life of a electron source in thermionic emission based sources is 100 to 1,000 hours. Okay, but in field emissions it is more than 2,000 to 5,000 hours. So because of that your maintenance of the equipment is reduced. नाहीतर काय होईल सारखं सारखं तुमचं मशीन बंद पडेल तुम्हाला ते ओपन करून क्लिअर ठीक करायचं परत वापरायला घ्यायचं. Here maintenance is less, but there are certain disadvantages also of field emission. One disadvantage is cost. कॉस्ट खूप हाय आहे ह्या अशा प्रकारच्या मशीनची एफईएसएम एफईटीएम ची ऍज कम्पेअर्ड टू द एसीएम और टीएम बिकॉज ऑफ रिक्वायरमेंट ऑफ व्हेरी हाय व्हॅक्युम्स. आता हे जेव्हा एवढा सारा आपण फील्ड अप्लाय करतोय व्हेरी हाय फील्ड अप्लाय करतोय खूप नॅरो बीम मध्ये करंट जनरेट करतोय तेव्हा तुम्हाला व्हॅक्युम कंडिशन्स खूप हाय ठेवावे लागतात. हिअर इफ यू लुक ॲट द ऑपरेटिंग व्हॅक्युम रिक्वायर्ड हिअर इज 10⁻⁶ to -5 Pascal. Okay, or millibar. But if you look at the field emission sources, the vacuum requirement is 10⁻⁹ to 10⁻10 millibar. So now to generate that much high vacuum, you need more pumps, good quality pumps, so that increases the cost of the machine. Cost of typical SEM or TEM is in the range of 1 to 4 crore. Okay. Cost of typical FE, SEM, FETM can be from 4 crore to 12 crores. So that is a tremendous change in the cost because of this machines. So whenever you are going for your analysis of your samples, you should know whether the place where you are going for analysis has a SEM or TEM, normal SEM or normal TM, or it has a FESEM or FETM. So first inquire that. If you have got FESEM or FETM, then you will get very good quality images. Okay, as compared to the SEM or TM because of all these factors that I am telling here. Cathode radius, current density, and brightness, and other factors. So these factors are very good here in FESM or FETM. So it is always better to use FESM or FETM in your imaging. If you are working on nanomaterials, if you are working on macron size particles or very big size particles, then you can go for SEM or TM, no problem. But for nanoparticles, especially less than 100 nanometer, you should go for FESM or FETM facility. So this is the difference in the electron sources. These are the thermionic emission sources like tungsten filament or lanthanum hexaboride filament. You can look at the tip. From this tip, the electron beam is emitted. Okay. Now the tip diameter here as well as here, it is very big. So because of that, you don't get very good quality images. But if you look at the field emission filament, the tip diameter is very small. It is in nanometers. So because of that, you get a very narrow beam. When you get a very narrow beam of electrons, you get very good resolution. Okay. Any doubts? कोणाला काही प्रश्न विचारायचे आहेत का? Am I audible?
Yes, sir. You are audible, sir.
Okay. So now we have compared why SEM and TM are better than the optical microscope. Then we have compared the electron sources like field emission sources and thermionic emission sources and how field emission sources are better. That's why FESM and FETM are better than SEM and TM. So that differentiation we have done. Now we'll see when an electron beam interacts with the sample, what kind of signals are generated because these signals give you the images and other information. One more factor is in optical microscope you only get images. तुम्हाला फक्त इमेजेस मिळतात ऑप्टिकल मायक्रोस्कोप मध्ये बट इन इलेक्ट्रॉन मायक्रोस्कोपीज लाईक इन एसीएम और टीएम along with images you get the more information about the sample like you get the information about its phase, its crystalline nature, okay, its composition, distribution of the composition in the sample. All that information, extra information is obtained in the electron microscopes that is not available in the light microscopes. So that is why this technique is important. So when an electron beam falls on the sample, when an electron beam falls on the sample, different interactions take place. First is some of the beam gets reflected. Okay. Some of the beam get back reflected and also some X-rays are generated. Okay. If the sample is thin enough, some beam can also penetrate through the sample. Okay. And during penetration also, it can generate certain signals like it can generate some elastically scattered electrons, some inelastically scattered electrons, and some directly transmitted electrons. Okay. Along with that, it can also generate X-rays in the transmission mode also. Now, based on whether you are capturing the signal on the reflected side or on the transmitted side, you get two kind of microscopies. When you capture the signals or the electrons and X-rays from the reflected side, then the microscopy technique is called as scanning electron microscopy or field emission scanning electron microscopy, SEM or FESM. When you are capturing the signals, when the electron beam is passing through the sample, then that microscopy technique is called as the TEM or FETM, transmission electron microscopy or field emission transmission electron microscopy. And the signal generated in SEM are secondary electrons, backscattered electrons, and X-rays. The Signal generated in TEM are elastically scattered electrons, transmitted electrons, inelastically scattered electrons, and X-rays. Okay. Now, these secondary electrons in SEM are useful for SEM analysis. Backscatter electrons are also useful for SEM analysis, while these X-rays are useful for chemical composition information. Okay. Similarly, elastically scattered electrons are useful for electron diffraction pattern generation. Directly transmitted electrons are useful for imaging, and inelastically scattered electrons are useful for a spectroscopy called as electron energy loss spectroscopy. Okay, we'll see one by one. So this is how an electron and matter interaction takes place when the electron beam is generated. Now the electron beam is generated from here. It is interacting with the sample. So this is your sample. Some visible light is generated in the reflection mode. Some X-rays are generated. Some secondary electrons are generated. Some backscatter electrons are generated. These are basically incoherent elastic electrons. And some auger electrons or Auger electrons are generated. And each kind of reflection gives a kind of signal. Secondary electrons gives one signal. Inelastically scattered, incoherent elastic scattered electrons or backscatter electrons are also generate one signal. Auger electrons generate one signal. X-ray generate one signal. If you apply the detectors, you can capture those signals and you can generate the images and other informations in the reflection mode. Similarly, incoherent electrons, coherent electrons, directed beam, X-rays are also generated in the transmission mode. And if you capture those signals also, you get the transmission mode electron imaging. So SEM and TEM are basically two imaging modes where how electron beam interacts with the sample is determined. Okay. If it is transmitting, it is TEM mode. If it is reflecting, it is SEM mode. But the machines for both the modes analysis are different. Okay. And the costs are all different. The resolutions or magnifications are different. TEM gives better magnification, better resolution as compared to SEM, but the cost is very high. SEM gives lesser magnification, lesser resolution, but the cost is less. Okay. Now we'll start with ACM, the scanning electron microscopy. Okay. Now scanning electron microscopy is considered much better than the optical microscopy in certain aspects. Which are those aspects? One of them is depth of focus. Depth of focus means in the length, how much can you focus your sample? आजकालच्या काळात पण तुम्ही बघितलं असेल, तुम्ही जेव्हा एखाद्या कॅमेराने इमेज घेता तेव्हा काही पार्ट पर्यंत तुम्हाला त्या इमेज मध्ये काही पार्ट तुम्हाला क्लिअर दिसतो, काही पार्ट ब्लर दिसतो. किंवा तुम्ही आजकाल तुमचा तो ब्लर मोड पण ऍक्टिव्ह करता. म्हणजे काय करता तुम्ही ब्लर मोड जेव्हा ऍक्टिव्ह करता तेव्हा बॅकग्राऊंड जो आहे तुमचा तो तुम्ही डिफोकस करता. फक्त जो तुम्हाला जो एरिया फोकस करायचा तेवढ्या एरियाज फक्त तो कॅमेरा फोकस ठेवतो, प्रॉपरली फोकस ठेवतो. सो दॅट इज बेसिकली द डेप्थ ऑफ फोकस. जेव्हा तुमचा डेप्थ ऑफ फोकस जास्त असेल तुम्ही खूप मागपर्यंतचं बॅकग्राऊंड जास्त क्लिअरली बघू शकता अलॉंग विथ द युअर ऑब्जेक्ट ऑफ इंटरेस्ट. जर नसेल पाहिजे तर डेप्थ ऑफ फोकस कमी असतो. सो ऑप्टिकल मायक्रोस्कोप मध्ये डेप्थ ऑफ फोकस हा फार कमी असतो ऍज कम्पेअर्ड टू इलेक्ट्रॉन मायक्रोस्कोप. सो दॅट इज वन व्हेरी इम्पॉर्टंट ऍडव्हान्टेज ऑफ this scanning electron microscope. And why that? Why is it possible? Because of the very high resolution. Okay, I'll show you some of the examples, then you will understand the concept. So this is one example of a screw. Sada screw ahe. Length of that screw is around 6 mm. Now if I try to look at this screw through optical microscope, what happens is I can focus either at the top of the screw or I can focus at the bottom of the screw, but I can not focus at the both places because of lesser depth of focus of optical microscope. त्याच्यात एवढं 6 mm पर्यंत फोकस करण्याची तुमच्या ऑप्टिकल मायक्रोस्कोप मध्ये कॅपॅसिटी नसते. तुम्ही वाटल्यास तुमच्याकडे जर लॅब मध्ये मायक्रोस्कोप असेल तर एकदा ट्राय करून बघा. Okay, so this is the disadvantage of optical microscope. Now if I look at the same screw through scanning electron microscope, I can focus on the top of the screw. I can also focus on the bottom of the screw. I can clearly see the morphological features at the top as well as at the bottom of the screw. Not only that, I can also see the lines or grooves on that screw in between. That means I am getting a very good depth of focus in scanning electron microscope. So this is the example from a real world. Okay. This is another example. This is from a small scale object. This is a macroscopic object. 6 mm is a very big size. Okay. This is a macroscopic object of surround few hundred microns. Okay. So this is some biological entity called as radiolarian. Okay. So it is basically a cage-like structure having some spikes. It is some organism. Okay. Now, if I look at it through the optical microscope, I can see some spikes. I can see little bit of cage structure, but I cannot see clearly the cage structure, the size and shape of that cage structure. I cannot see it clearly. Same is the case for spikes. Now, if I look at the same organism through electron microscope, I can clearly see the spikes. I can, in fact, I can clearly see the tips of the spikes clearly. I can also see through that cage structure inside, and I can clearly then understand what is the structure of this organism. Okay. Again, this is because of the better depth of focus of SEM as compared to the optical microscope. So that is why for lots of applications, SEM is preferred as compared to the optical microscope. Now, if you look at the instrument of SEM, so this is a typical instrument available in the lab, and this is the schematic of that instrument. So it consists of an electron gun, okay, where you have to apply certain potential and then bring out the electron beam. Okay, then there is an aperture through which the electron beam comes out. Condenser lens is there. Then scanning coil is there, which control the magnification. Then there is an objective lens, again for focusing and defocusing of the beam. Then the beam falls on the sample and signals are generated. What kind of signals are generated? Here we have given. Secondary electrons are generated and some backscattered electrons are generated and some X-rays are generated. So these are the three main signals that are generated when an electron beam falls on the sample and is getting reflected. There are other signals also like Auger electrons and visible light, but they are not useful for imaging. So they are not captured. Detectors don't capture them. Okay. Now this scan coil is very important because this scan coils basically scan help in scanning the electron beam on the sample. So that is why it is called as a scanning electron microscopy because this coil scan the sample. Okay, it is like to your TV screen also. In your TV screen also, when you look at the TV screen and you are seeing the image, basically that electron beam in your TV screen is scanning that picture tube, and you are getting the signal. The similar scanning occurs here also. Then, as I told you, we have to capture two important signals. Basically, three important signals: X-rays, secondary electrons, and backscatter electrons. So there is one detector for the secondary electrons. There is one detector for backscatter electrons. There is one detector for EDS also, the X-rays, but that is not shown here in the schematic, but it is there in the machine. I'll show you. So this is that column. This electron beam and this condenser lens, objective lens column is this one. So electron beam is generated here and then it passes through the sample through this. Now your sample holder is this one. So through this holder, we have to insert the sample in the chamber. Okay. Then this is one detector. Then there is another detector here. And this EDS detector is this one, that X-ray detector. So it is at the back side of this machine. Now, how do we get an image? So this is your sample and this is your area of interest for which you have to image the sample. Okay, so for this square, we are now generating the image. So we'll see how the electron gun falls on this. Now, electron gun generates the electron beam, and now this square is also divided into I can say in terms of pixels. तुम्हाला पिक्सेल्स मध्ये लवकर कळेल कारण की आपले जे कॅमेरा असतात त्याची मॅग्निफिकेशन आपण पिक्सेल मध्ये देतो किती मेगापिक्सेलचा कॅमेरा आहे सो बेसिकली पिक्सेल म्हणजे काय असतं तर तुमचा जो इमेजचा एरिया आहे तो तुम्ही किती किती पार्ट्स मध्ये डिवाइड करू शकता जितका जास्त पिक्सेल्स असतील तेवढं तुम्ही छोट्या पार्ट मध्ये डिवाइड करू शकता तेवढा तुम्हाला जास्त रिझोल्युशन मिळेल okay so you can consider these as the pixels on which the electron beam is falling on the sample and generating the signals. सो हे पिक्सल साईज जेवढी छोटी तेवढे जास्त सिग्नल तुम्हाला जनरेट होतील, जेवढी मोठी तेवढे कमी सिग्नल जनरेट होईल, तुम्हाला तेवढी कमी क्वालिटीची इमेज मिळेल. ओके, सो नाउ इलेक्ट्रॉन बीम इज फॉलिंग ऑन द वन पार्ट ऑफ द सॅम्पल. ओके, secondary electrons are getting generated and they are detected by the detector and the data is fed to the computer, say 156 electrons. Now it will scan to the next spot. Again, secondary electrons will be generated, detected by the detector, and it will count the number of electrons. And then accordingly, here in the image zone, some contrasts are getting generated based on how many number of electrons are captured. This process will go on occurring, and accordingly, based on the contrast that is getting generated, based on the number of electrons, you will get the image in the SEM mode. Okay. Sorry. So what kind of signals are generated? I already told you: secondary electrons, backscattered electrons, and X-rays. So secondary electrons give you the information about the surface topography, surface morphology जी असते ना, ती information mostly secondary electrons ने generate होते. These are basically low energy electrons, but they provide high resolution. Why? Because they get reflected from a very small top surface of the sample. म्हणून ते top surface ची जास्त information carry करतात. So that is why you get very good resolution. Their penetration depth is small. Okay. Backscattered electrons, they basically provide information mainly about the chemistry. Chemistry means phase. Oh, okay. Phase means presence of different compositions are there. If there are different compositions present in the sample, say some area is having high atomic number elements, some area is having low atomic number elements, then the differentiation between those two can be generated by a contrast. That chemical contrast is generated by these backscattered electrons because they penetrate more in the sample, and heavy atoms will backscatter them more, and lighter atoms will not backscatter them more. ओके, तुम्ही 12वी मध्ये रुदरफोर्डचा एक एक्सपेरिमेंट केला असणार आहे किंवा स्टडी केलेला असणार आहे 12वी मध्ये. रुदरफोर्ड बॅकस्कॅटर्ड रुदरफोर्ड ॲटॉमिक मॉडेलचा एक्सपेरिमेंट केलेला असणार आहे तुम्ही 12वी मध्ये. त्याच्यात काय असतं, एक इलेक्ट्रॉन बीम गोल्डच्या ॲटम फॉईल वरती बंबार्ड होतो आणि काही सिग्नल जनरेट होतात. त्याच्यावरनं त्यांनी ॲटमचं मॉडेल काढलं. ते कसं काढलं होतं की ॲटमच्या सेंटरमध्ये न्यूक्लियस आहे, त्याच्या आजूबाजूला इलेक्ट्रॉन्स पर्टिक्युलर ऑर्बिट मध्ये फिरतायत. ओके, आता जे जो ॲटॉमिक नंबर असेल त्याच्यानुसार त्याचं नंबर ऑफ जे इनर्शियल इलेक्ट्रॉन्स असतील ते जास्त असतील, हेवी असेल तो ॲटम. ओके, जेवढा हेवी ॲटम असेल त्याच्यापासून बॅकस्कॅटर इलेक्ट्रॉन जास्त तयार होतात. सो त्याच्यामुळे रुदरफोर्डला त्याच्या एक्सपेरिमेंट मध्ये बॅकस्कॅटर इलेक्ट्रॉन्स पण मिळाले होते, आणि मेजॉरिटी ऑफ द इलेक्ट्रॉन्स मात्र डायरेक्टली निघून जातात. का? कारण की इलेक्ट्रॉन्स लाईटवेट आहेत. अँड देअर ॲटम्सच्या मध्ये जे ऑर्बिटल्स आहेत त्याच्यात गॅप्स आहे, म्हणून ते इझिली काही निघून जाऊ शकले, काही स्कॅटर झाले आणि काही बॅक स्कॅटर झाले. जे स्कॅटर झाले त्यांचं काय झालं की ते इंटरॅक्टेड विथ द आउटर शेल इलेक्ट्रॉन्स. ओके, आणि आउटर शेल इलेक्ट्रॉन निगेटिव्हली चार्ज आहे, इनकमिंग इलेक्ट्रॉन निगेटिव्हली चार्ज आहे, त्यांच्या रिपल्शन होऊन ते निघून गेले थोडेसे बेंड होऊन. ओके, बॅक स्कॅटर मध्ये मात्र ते इंटरॅक्ट झाले त्या ॲटम सोबत आणि नंतर ते परत गेले बेंड होऊन बॅक. Okay, so that kind of contrast because of the heavy atoms and lighter atoms can be generated in BSE mode. And along with that, when an electron beam passes through the sample, it can penetrate inside. It can penetrate up to K shell, L shell of the atom. K shell, L shell electrons जे असतात ना ते atomला tightly bound असतात as compared to the जे outer shell electrons असतात. Because of that, what happens is, if that high energy electron penetrates and interacts with the K shell electron, it can knock out that K shell electron. Now, to take place of that K shell, knocked out K shell electron from the L shell or M shell can jump to that place and fill that orbit. But since it has jumped from the L shell or M shell, it will not be stable and it will come back to its original position. In the process, it will generate some X-rays. Now these X-rays will provide the information about the K shell energy level, L shell energy level or M shell energy level. आता प्रत्येक ॲटमची जी K shell, L shell, M shell energy levels असतात, they are different. ते फिंगरप्रिंट सारखं असतं. प्रत्येकाचा फिंगरप्रिंट सेम नसतो. तसंच प्रत्येक एलिमेंटचा के शेल, एल शेल, एम शेल, एनर्जी लेवल जे असतात त्या वेगळे असतात दुसऱ्या एलिमेंट पेक्षा. बेस्ड ऑन दॅट यू कॅन कन्सिडर द केमिकल कंपोजिशनल इन्फॉर्मेशन. ओके, जे एक्सरेज मधनं जनरेट होते. दॅट टेक्निक, द स्पेक्ट्रोस्कोपी टेक्निक इज कॉल्ड एज एनर्जी डिस्पर्सिव स्पेक्ट्रोस्कोपी और ईडीएस. दॅट इज बेस्ड ऑन द एक्सरे जनरेशन. ओके. सो हे 3 सिग्नल असतात, हे महत्वाचं लक्षात ठेवा. Now what kind of information I can obtain from a typical ACM image? तुम्ही ACM साठी गेलात, ऑपरेटरने तुमच्या सॅम्पलची इमेज तुम्हाला दिली, तुम्हाला काय इन्फॉर्मेशन मिळते, तुम्ही काय इंटरप्रिटेशन करू शकता, हे मी या इमेज मधून तुम्हाला सांगतो. सो दिस इज अ टिपिकल ACM इमेज. इफ यू लुक at this image, I am seeing some structures. What kind of morphology is there? It is rod-like morphology. रॉड सारखे दिसतात, पार्टिकल जे आहेत ते रॉड सारखे दिसतात, वेगवेगळ्या डायरेक्शनला ते ओरिएंटेड आहे. Along with that, at the bottom, you will see some extra information. What you see is, you will see one scale with 2 micron written here. Now, depending on magnification, it can be 2 micron, 1 micron, 500 nanometer, 100 nanometer, even 10 micron, 40 micron, depending on what magnification you are going. So that information is given here, magnification. So here it is 50,000x, means this image is magnified 50,000 times more as compared to the original image. ओके, सो 50,000 टाइम्स आपण मॅग्निफाय केलेली आहे इमेज. ऑप्टिकल मध्ये तुम्ही बघितलं होतं टिपिकली कितीपर्यंत जातं, 500 ते 1500 मॅग्निफिकेशन, 501 ते 1501. इथं ऑलरेडी आपण 50,000 ला गेलो आणि याच्यावरती पण जाऊ शकतो. देन मोड, विच मोड इज देअर? मोड दे हॅव रिटन इज AC. AC मीन्स सेकंडरी इलेक्ट्रॉन्स दे आर कॅप्चरिंग. ओके. टिल्ट, कधी कधी काय असतं, स्पेशली इन केस ऑफ फिल्म्स, you will not get very good morphological information if you have got a flat surface. Then in that case, you can tilt your sample. So that tilt information, but here they have not tilted the sample. That is why the tilt is 0 degree. Okay. Then detector, which kind of detector is there? So that detector name is there. Okay. Then one more factor that they have given here is working distance. The working distance is basically the distance between the sample and the electron beam. If you go closer to the sample, you will get better signal, you will get better images, better quality images. Okay. But the one problem with working distance sometimes is your electron beam or electron tip can crash into your sample. So you have to be very careful. So that's why you have to mention working distance also. If you are not getting very good quality images, very good signal, in that case, you can request the operator to reduce the working distance. त्यांना म्हणू शकता तुम्ही की थोडंसं अजून जवळ जा सॅम्पलच्या, 11च्या ऐवजी 10ला जा किंवा 9ला जा वर्किंग डिस्टन्सला. देन यू मे गेट गुड क्वालिटी इमेजेस. And the last important factor that you are seeing here is HV. How much voltage you have applied. Typically, ACM imaging is done from 1 kilovolt or range is around 0 kilovolt to 30 kilovolt. Okay, but some machines have got the capacity up to only 20 kilovolt, some have got up to 30 kilovolt. Okay, so 0 to 30 kilovolt is the typical range of ACM imaging. So here they have applied 20 kilovolt potential. Now this potential is sufficient for inorganic samples. ओके. जेव्हा इनऑर्गॅनिक सॅम्पल असेल तेव्हा तुम्हाला थोडं हाय पोटेन्शियल अप्लाय करावं लागतं, कारण की स्पेशली इफ यू आर युझिंग non-metallic samples, then you have to apply high potential, because then getting the electrons backscattered or scattered from this kind of samples is difficult. For biological samples, if you apply this much of potential, it will get damaged. Or for polymeric sample, for organic samples, if you apply this much high potential, it will get damaged. Inorganic samples astil, ceramics astil, metals astil, they will not get damaged by this kind of potential. Okay. So when you are using inorganic or ceramic or metallic samples, you can apply high potential. Even you can go higher than this if the machine has got the capacity, say 25 kilovolt or 30 kilovolt. But if you are using some biological sample or some organic sample or some polymeric sample, then you can request the operator to reduce this potential. You can reduce to 10 kilovolt or 5 kilovolt. In some cases, people go up to 2 kilovolt. Okay. So this kind of information is obtained from the ACM image. I'll give you some examples of these SEM imaging modes and the difference between secondary electron detector and backscatter electron detector. Most of the SEM imaging is done using secondary electron mode because it gives better resolution. Okay. So for example, this image also, this is done in SEM SE mode, secondary electron mode, because you just need information about the surface morphology. So जेव्हा surface morphology ची information पाहिजे असेल तेव्हा तुम्ही SE mode वापरा. But if your sample contains multiple elements or elements having different atomic numbers, काही elements heavy आहेत, काही elements light आहेत, आणि तुम्हाला त्यांचं distribution बघायचं आहे, chemistry बघायची आहे त्यांची. In that case, you can use that BSE mode. So त्याचे मी काही examples इथे दाखवतोय. This is a typical solder ball. Soldering साठी जे वापरतात electronics मध्ये, that material is basically an alloy called as lead tin. It is an alloy of lead and tin. Now lead is heavy element, tin is low atomic number element. Okay, so it can generate this backscatter electron contrast. Lead will backscatter more electrons, tin will backscatter less electrons. So there will be a contrast in the image, elemental contrast in the image. So this is SE mode imaging. You can see here, this is a typical lead ball, SE mode imaging. You are seeing some difference, some contrast is there, little bit contrast is there from here and here. So this darker can be lead, lighter one can be tin. Okay, but if you want better quality image, then you can go for BSE mode. If you request the operator that I want the BSE mode image, here you can see this is BSE mode image. Then operator can switch from AC mode imaging to the BSE mode imaging. The only disadvantage of BSE mode imaging is the resolution of BSE mode imaging is not very good. Okay, but the contrast is good. Now here you can see clearly the atomic contrast. The brighter part is very bright, the darker part is very bright, very dark. So because of that, you can clearly identify the difference between lead and tin in the sample. So that was one example. This is another example. This is a metallic sheet. Okay, but that metallic sheet is corroded at certain points. Now, if you look at this is AC mode imaging. In AC mode imaging, you will not observe any appreciable corrosion. At certain points like here and here, you may feel that yeah, some corrosion is there. Okay, but now if you look at the same sample in BSE mode, you can see the same sample is there. It is in BSE mode. You can see the corrosion spots like this dark region basically is all corrosion part, corroded part. Okay, which you can clearly see in BSE mode imaging. Okay, this is a third example. This is basically alumina sheet. Okay, and on that or alumina powder, micron size alumina powder. On top of that micron size alumina powder, platinum nanoparticles are sprinkled or loaded. Okay, now if you look at this SE mode image, secondary electron mode image, you will not see the difference between alumina and platinum. You will not see the distribution of platinum on that alumina powder. Now, these kind of loaded particles are useful in various catalytic applications. Various chemical reactions can be done by using this kind of catalyst. Now, for that effective reaction, this platinum distribution is very important on that alumina. But in SE image mode, you will not see that kind of distribution. In BSE, you can clearly see that. The brighter particles are basically platinum because platinum is heavy. Okay, so it is giving good contrast. Lighter is aluminum. So aluminum is at low atomic number element. So it is not giving good contrast. So we are getting the distribution of platinum on the alumina. So in certain cases like this, you can go for BSE mode imaging. But if you want to just see the morphology, surface morphology, you should always go for SE mode imaging. So we have discussed about SE mode imaging, BSE mode imaging. The third important aspect now is spectroscopy. Okay, the spectroscopy in SEM or TEM mode is called as energy dispersive X-ray spectroscopy because it is based on X-rays. X-rays are also dispersed, okay, with certain energies, and those X-rays are captured as signal, and then they are plotted, and then the energy levels are matched with the binding energies of K shell, L shell, M shell of elements, various elements, and based on you can identify the presence of elements in your sample. Okay, so this is a compositional analysis. Now it is called in various names by different machines. काय आहे मशीन्स जे मॅन्युफॅक्चरर आहेत ना त्यांनी त्यांच्या या टेक्निकला वेगवेगळी नावं दिली आहे. काही लोक त्याला ईडीएस म्हणतात, एनर्जी डिस्पर्सिव्ह स्पेक्ट्रोस्कोपी. काही लोक म्हणतात ईडीएक्सएस, एनर्जी डिस्पर्सिव्ह एक्सरे स्पेक्ट्रोस्कोपी. काही लोक म्हणतात एक्सईडीएस, एक्सरे एनर्जी डिस्पर्सिव्ह स्पेक्ट्रोस्कोपी. आणि काही लोक म्हणतात ईडीएक्स, एनर्जी डिस्पर्सिव्ह एक्सरे अनालिसिस. त्याला ईडीएक्स पण म्हणतात काही लोक, एनर्जी डिस्पर्सिव्ह अनालिसिस ऑफ एक्सरेज, ईडीएक्स. सो जेव्हा तुम्ही तुमच्या सॅम्पलच्या अनालिसिसला जाणार तेव्हा तुम्ही ऑपरेटरला सांगा की मला केमिकल कंपोजिशन माहिती करून घ्यायचं आहे, त्यासाठी मला ईडीएस वापरायचं आहे किंवा ईडीएक्स वापरायचं. ऑल नेम्स आर डिफरंट, टेक्निक इज सेम. ओके, ओनली द ऍज पर द मशीन these नेम्स आर डिफरंट. So how X-rays are generated? Basically, an electron interacts with the sample. It has knocked off the electron from the K shell. The L shell electron has jumped to this place. In the process, it has emitted a photon. That photon is having some energy in the form of an X-ray. सो एक्सरे जे आहेत ते दोन प्रकारचे असतात, एक कॅरेक्टरिस्टिक्स एक्सरेज आणि एक कंटिन्युअस एक्सरेज. कंटिन्युअस एक्सरेज हे कंटिन्युअस निघतात सॅम्पल मधनं बट दे डोंट कॅरी एनी एनर्जी. कॅरेक्टरिस्टिक्स एक्सरेज बेसिकली कॅरी द एनर्जी ऑफ पर्टिक्युलर शेल. के शेल, के शेल मध्ये पण के तुम्हाला जर आता डिजेनरेट ऑर्बिटल थेअरी वगैरे तुम्ही तुमच्या केमिस्ट्रीमध्ये स्टडी केलं असेल तर के शेल पण काय एक एक्स्ट्रा नसते, एक सिंगल शेल नसते. इट इज K1, K2 और के अल्फा 1, के बीटा, के अल्फा, के बीटा, के अल्फा 1, के अल्फा 2 असं वेगवेगळ्या सबशेल्स असतात. त्या सगळ्यांच्या एनर्जी लेवल्स तुम्ही इथं कॉम्प्युट करू शकता. ओके, and based on from which energy shell the electron is jumping, you will get certain signals here, and then based on those energy level signals you can identify the presence of elements in your sample. So this is how a typical X-ray EDS spectrum looks like. खाली एनर्जीचा हे असतो, यू कॅन सी द एनर्जी इन केईव्ही, आणि इकडे वाय साइडला इंटेन्सिटीचा बार असतो. नाउ फॉर दिस पर्टिक्युलर सॅम्पल इट इज शोइंग सीआर, सीयू, अल्युमिनियम, सिलिकॉन, अगेन सीआर, अगेन सीयू. वाय सीयू टू टाइम्स, वाय सीआर टू टाइम्स? जर तुमचा एनर्जीचा स्पेक्ट्रम आहे, एलिमेंटचा प्रेझेन्स दाखवतोय, तर एकच पीक असायला पाहिजे ना. बट यू विल नॉट फाइंड वन पीक बिकॉज ऑफ धिस. You are not getting electron or X-ray emission only from one K shell. You can get it from K alpha, K beta. You can get it from M alpha, M beta, L alpha, L beta. So that is why you are getting these kind of different based on the energy level of that particular shell, K shell, L shell, M shell. You are getting different peaks of same element. Like chromium चे दोन पीक आहेत, कॉपर चे दोन पीक आहेत, सिलिकॉन चे पण असू शकतात, पण मे बी दे आर आउट ऑफ दिस एनर्जी रेंज. And from these energy levels and from these intensities and any area under the curve and other analysis, you can know quantitatively as well as qualitatively the presence of elements. Qualitatively तुम्हाला या ग्राफवरूनच कळेल की कुठले कुठले एलिमेंट्स प्रेझेंट आहेत तुमच्या सॅम्पल मध्ये, अशा प्रकारच्या ग्राफमध्ये, नॉट या ग्राफवरनं, अशा प्रकारच्या ग्राफवरनं. आणि क्वांटिटेटिव्हली तुम्हाला पर्सेंटेज मध्ये पण कळू शकतं, ऍटॉमिक पर्सेंट, वेट पर्सेंट. द ओनली फॅक्टर इज एनर्जी डिस्पर्सिव्ह स्पेक्ट्रोस्कोपी इज लोकलाइज स्पेक्ट्रोस्कोपी. ते एका पर्टिक्युलर रिजनचं तुम्ही अनालिसिस करता. सो यू कॅनॉट अप्लाय दिस अनालिसिस टू द एंटायर सॅम्पल distribution if your sample distribution is not homogeneous. So it is not called as a quantitative technique, it is called as a semi-quantitative or semi-qualitative technique. कारण तुम्हाला 100% यातनं रिझल्ट मिळत नाही, पण एक आयडिया येऊन जातं, स्पेशली इफ युअर सॅम्पल पर्सेंटेज इज मोर दॅन 1%. म्हणजे कुठल्याही एलिमेंटचं प्रेझेन्स जे आहे तुमच्या सॅम्पलमध्ये त्याचं मोर दॅन 1% असेल तर यू विल गेट व्हेरी गुड ॲक्युरेट रिझल्ट ॲज कम्पेअर्ड टू इफ इट इज लेस दॅन 1%. So different kind of X-rays are generated, characteristics X-rays and continuous X-rays. So continuous X-rays basically form the background in this spectroscopy. So you have to minus this background and then you have to do the quantitative analysis. Here you can see SiK alpha peak is there, aluminum K alpha peak is there, magnesium K alpha peak is there. Fe, for Fe it is L alpha. For oxygen again it is K alpha. So you will get the information about the peaks, their K alpha position, L alpha position, And based on that, all analysis, you can also quantitatively know the presence of elements in the sample. This technique is called as energy dispersive spectroscopy, EDS. Okay. Now here in this, I'm giving some examples how it is useful. So this is one sample. This is the SEM image of that sample. From that sample, we are seeing different regions. Like this is one region where some contrast is there. This is another region where the contrast is entirely different. This is third region. Again, the contrast is different. Fourth, this is very dark region. Fifth, sixth, seventh. So different regions are there in the sample. That means there can be different compositions in different regions of the sample. How I will know that? So what I will do is I'll do EDS analysis, but I will not do the analysis on the entire sample. What I will do is analysis of EDS in one region of the sample. That means I'll focus my beam on that region only. And then I'll get this kind of a graph. Then I'll focus my beam on this particular region. I'll get another graph. Okay, so this is the graph for point 1. This is the graph for point 2. Now in point 1, what I am observing? I am observing the presence of zirconium, silicon, and aluminium. Okay. Now at point 2, I am observing silicon. I am also observing aluminium, but I am not observing zirconium. Okay, so zirconium is absent in my sample in this particular region. Huh? But I am also observing few other elements, extra elements. What are those? Potassium is there, iron is there, to a small extent, vanadium is also there. Titanium is also there in the very small quantities. Okay, so that means the chemical composition of this region and this region is different, and I can know it from this graph. Not only qualitatively, I can also know the percentage. I'll show that also. So this is one way of analysis, EDS analysis, from the graphs by doing the analysis at particular points. But if I want to map the entire image and I want to know the distribution of various elements in that image, entire image, instead of doing this point by point analysis, I can do the entire image analysis also. That is done by another technique called as mapping, एलिमेंटल मॅपिंग. म्हणजे प्रत्येक एलिमेंटला तुम्ही मॅप करू शकता. हे का करू शकतो मी? कारण की माझा जो बीम आहे तो रास्टर स्कॅन करतोय. रास्टर स्कॅन करताना जर एक्सरे जनरेट होत आहेत तर ते पण मी रास्टर स्कॅन मध्ये कॅप्चर करू शकतो त्यांच्या एनर्जीज. ओके, अँड देन दोज एनर्जीज कॅन बी प्लॉटेड as different elements, right? So that is done here. So this is for carbon. So carbon is distributed throughout. Oxygen, you can see oxygen distribution in particular regions. Same image. I have done the mapping of the same region. So oxygen is more or less present everywhere. Sodium is also more or less present everywhere. But magnesium, if you look at this image, magnesium is present in this particular region of the sample. That means magnesium is present in this region. It is absent here and absent here. Now, if you look at aluminium, again, like magnesium, aluminium is also present only in this region of the sample. Now, if I look at silicon, silicon is absent where magnesium is present. Like magnesium is present here, but silicon is absent. Aluminium is present here, but silicon is absent. Where silicon is present? Silicon is present only on the corners, like these corners. Like silicon is present in this region and in this region. And you can see the contrast. The contrast of this region and this region are same, but they are different from this region. Okay. So you can correlate your data. Similarly for calcium. Calcium is also present where aluminum and magnesium are present. Okay. Iron is present again in the same region where magnesium and aluminum and calcium are present. But if you look at here, in this region, zirconium is present. Okay. And that is why in this EDS graph, for this region, you are getting zirconium peak, but you are not getting zirconium peak in this region 2. Because zirconium is present only in this region. So now mapping also now confirming that. So you can do EDS graph analysis on EDS mapping analysis. So whenever you are going for SEM analysis, you can ask the operator if you have got this kind of sample containing multiple elements and their distribution if you want to know. then you can ask the operator about this EDS spectroscopy with mapping, elemental mapping. So keep this word in mind, elemental mapping. So you can ask the operator or you can request the operator that I want to do this elemental mapping also. So please provide that data also. This is another example. This is for silicon. This is a silicon wafer kind of thing, and it has got some holes. Okay. And now we want to study the distribution of elements in those holes. So again, elemental mapping was done. So this is elemental mapping image for silicon. So silicon is present everywhere except at certain holes. Okay. And the scale is 300 micron. Now at those holes, iron is present. You can see here in the mapping. Iron is not present at other places, but at those holes, iron is present as an impurity. Okay. So this kind of distribution study can be done by using mapping, X-ray mapping or EDS mapping. This is one more example. Again, this is the SEM image of one sample. Here again, you can see contrast. One region is there, another region is there. This is third region, fourth region, and fifth region. Now, when mapping was done for this image, it was observed that this first region and this second region and third region contained silicon, but cerium, but it was absent in those two contrasting regions. Okay. Now, if you consider iron was present in this region, this contrast region, and this region, but it was absent at other places. But strontium, surprisingly, it was present here, here, but along with that, it was present here also. That is why you can see little bit change in the contrast in these two regions because of the presence of strontium here and not here. Okay. So this kind of distribution is again very important in analysis. This is one example of SEM analysis. So this is again SE mode, secondary electron mode image of the sample. Now EDS was done at three regions of the sample. Spectrum 1 was taken here, spectrum 2 was taken at this point of the rod, and spectrum 3 was taken at third point of the rod. At each point, the distribution of zinc, oxygen, and silicon is different because the doping is not uniform on the rod. You can see here the silicon doping is around 1.9 atomic percent. At spectrum 2, it is around 1.3 atomic percent. And at spectrum 3, it is around 1.6 atomic percent. So distribution of silicon is not uniform throughout the sample. So this kind of information can be obtained by using SEM. This is another example of gold nanorods. These are gold nanorods having various sizes. Here again, you can read the scale properly. Scale is 300 nanometer. That means the distance between this and this line is around 300 nanometer. Now from this line, you can find out the particle size. For example, this nanorod may be around 40 to 50 nanometer in size, length, and thickness may be around 5 to 10 nanometer. Okay, roughly. I'm not doing exact calculation. Magnification for this is around 3 lakhs. And the mode is AC. Now, from this, you can do the particle size counting, length counting, means rod length counting, and plot its distribution, rod thickness counting, plot its distribution, and correlate with other techniques. For example, here you are getting a nanorod-like sample. Now, if you look at the UV visible spectra of that, surface plasma resonance spectroscopy, maybe सुधीर सरांनी तुम्हाला शिकवलं असेल आधीच्या लेक्चर मध्ये. तर surface plasma resonance मध्ये whenever you are having a rod-like structure, you will get two peaks because there is one SPR peak along the rod length and one SPR peak along the thickness. So you are getting this peak, particular peak, due to this length, rod length, and this smaller peak because of the thickness. Thickness is smaller. Okay. So you can correlate your data, SEM data, with your optical microscopy data. Okay. So this kind of correlation is very important. Whenever you are doing any analysis, and if you are doing SEM and some other studies, you can correlate whatever property you are obtaining with your SEM data and vice versa also. Your other data also can be correlated with not only SEM, other techniques also. That is why you have to do multiple analysis of your sample, like you have to do XRD analysis, you have to do SEM analysis, Raman spectroscopy analysis, UV visible spectroscopy, FTI spectroscopy, because then you can correlate the analysis of various data and then you can find out a bigger picture, better picture, okay, which you may not get using only one technique. This is our example at CIMET. Again, these are serious nanoparticles. Scale is 5 micron here in this first case. The magnification is 11,000. The working distance is 8.2 mm. And the applied potential is 5 kilovolt. Okay. Now the same image is magnified. Now the scale is 500 nanometer. Now the entire scale is 500 nanometer and it is divided into 10 lines. Means the distance between these two lines is around only 50 nanometer. From that 50 nanometer, you can calculate the particle size. Now I am not getting very good resolution here. I am not able to distinguish the particles clearly. Why? There is one problem with that because I am using very small potential, 5 keV potential I am using. So because of that, I am not getting very good signal. Okay. So that's why you have to be careful while doing such kind of analysis. Now in this case, I am getting very good quality images even at 500 nanometer resolution. Why? Because I am applying a potential of 10 keV. Because of that 10 keV, more higher energy electrons are getting emitted, and because of that I am getting very good signal. Okay. Now this example shows I am doing the analysis at various magnifications like 11,000 magnification, 25,000 magnification, 50,000 magnification, and 1 lakh magnification. Okay. Other parameters are same, like the potential applied is same, working distance is same. It is 5.7 mm. So again, because of that 5.7 mm working distance as compared to 8.2 here, I am getting even better quality images. So this is a flower-like structure. एक फुलाच्या सारखं structure आहे. The length of this flower-like structure from this scale can be around 5 to 7 micron. Okay. Then you will say this is nano, this is not nano, this is micron size particle. Okay. But you have to do further analysis for that. Now, if I magnify a region of this flower-like structure, now I am seeing the petals. Now the scale is 200, 2 micron, means the distance between these two lines is 200 nanometer. Now, if I compare this petal, the thickness of that petal is less than 200 nanometer. So I'll magnify it even further to see the petal's length. Here I can see the length of the petal at least. It is around 1.5 micron, length of the petal, not thickness. At magnified image, I can see the thickness of the petal. Now this scale is 1 micron, so distance between these two lines is 100 nanometer. Now if you look at this here, look at this petal thickness, or here it is around 100 to 200 nanometer thick. Okay. Again, we may feel that it is not nanoscale feature, but this petal is not made up of a sheet. It is made up of tiny particles. छोटे छोटे particles agglomerate झालेत. So again, I magnified further. I went 1 lakh magnification. Scale is 500 nanometers. So distance between these two lines is 250 nanometer. Now, if you look at these particles, the particles are 50 to 100 nanometer in length or size, diameter. Some rod-like structures are also there. The thickness of those rods is also 70 to 80 nanometer. That means these are nanoparticles coming together, agglomerating and forming a petal. Now these petals are forming together a flower-like structure. म्हणजे पार्टिकल्स एकत्र आले, त्यांनी एक शीट लाईक स्ट्रक्चर तयार केलं, एक पाकळी तयार केली, अशा बऱ्याच पाकळ्या एकत्र येऊन हे फुलासारखं स्ट्रक्चर तयार झालं. सो अशा प्रकारचं इंटरप्रिटेशन आपण या सॅम्पलचं करू शकतो. जेव्हा आपण एसीएम अनालिसिस कन्सिडर करतो, सॅम्पल प्रिपरेशन इज व्हेरी इम्पॉर्टंट. Based on your sample, what kind of sample you have prepared, you have to do a precise sample preparation. जर तुमचं सॅम्पल कंडक्टिंग असेल तर सॅम्पल प्रिपरेशन मध्ये जास्त त्रास नसतो. बट इफ युअर सॅम्पल इज नॉट कंडक्टिंग, से इन्सुलेटिंग मटेरियल आहे, काही सिरॅमिक मटेरियल आहे, ओके, देन देर आर इश्यूज. That occurs because of the charging. Charging म्हणजे काय होतं बेसिकली, हे तुम्हाला मी इथे दाखवतोय. दिस इज वन सॅम्पल, दिस इज अनदर सॅम्पल. आता इथे तुम्हाला थोडा ब्राईट रिजन दिसतोय, बाकीचा रिजन ब्राईट नाही. आणि हा एक असा एक बँड पण दिसतो इथं. रिझोल्युशन पण एवढं छान दिसत नाही. या इमेज मध्ये पण तसं तुम्हाला इथं एजला जो आहे हा ब्राईटनेस दिसतोय. हा ब्राईटनेस ॲटॉमिक कॉन्ट्रास्टचा नाहीये. इट इज नॉट ड्यू टू ॲटॉमिक कॉन्ट्रास्ट, इट इज बिकॉज ऑफ द चार्जिंग इफेक्ट. व्हॉट हॅज हॅपन्ड इज this sample is not conducting, even this sample is not conducting. आपण जेव्हा हे सॅम्पल तयार करतो एसीएम साठी वगैरे, तेव्हा काय करतो की आपण सॅम्पलला कास्ट करतो कशावर तरी. आयदर इट इज अ कार्बन कंडक्टिंग कार्बन टेप और इट इज अल्युमिना स्टब. अल्युमिनाची एक शीट असते त्याच्यावरती आपण कास्ट करतो. ते कास्ट करताना जर तुमच्या सॅम्पलला प्रॉपर ग्राउंडिंग झालं नाही अल्युमिनियम पर्यंत सॉरी, तर त्या केसमध्ये जो इलेक्ट्रॉन बीम आहे तो निगेटिव्हली चार्ज आहे. तुमचा जो सरफेस आहे तो इन्सुलेटिंग आहे, तो त्या इलेक्ट्रॉन बीमला ग्राउंडिंग नाही मिळालं तर तो करंट पास नाही होणार, फ्लो नाही होणार, तो त्या सरफेसवरती राहणार. आता सरफेसवरचा इलेक्ट्रॉन्स and the incoming electron beam both are negatively charged. They will try to repel each other. Because of that, what will happen is electron beam will deflect, and that deflection causes this kind of effects. हे जे इफेक्ट्स दिसतात ना, हे this is all charging. तो चार्ज सरफेसवरतीच राहतोय. So what we have to do is you have to provide a proper grounding to your sample. Now that grounding is done by different ways. One of them is coating the sample with some conducting layer, very thin conducting layer, maybe 1 nanometer, 2 nanometer thin conducting layer. If you put on your sample, then it will get a grounding path and electron beam will not stay on the sample. Okay. So that is done by using a sputter coating. And त्याच्यासाठी जे कोटिंगची जी लेअर असते त्यासाठी जे टार्गेट वापरतात, that is either gold palladium or it is carbon. That is for powder sample. If you have got a film like sample, surface वरती तर coating होईल, पण त्या thickness चं काय? Thickness will be again insulating. In that case, you have to do a grounding line with a silver paste or silver or carbon paste. एक पेस्ट लावली जाते, so that वरचं तर तुम्ही कोटिंग केलं याने स्पटरिंगने, पण त्या जो थिकनेस आहे तिथलं ग्राउंडिंग करण्यासाठी ही पेस्ट किंवा हे लावलं जातं, सिल्वर पेस्ट किंवा कार्बन पेस्ट. बिकॉज ऑफ दॅट द इलेक्ट्रॉन्स विल गेट ग्राउंडेड टू द लोअर सबस्ट्रेट. ओके. सो अशा प्रकारे सॅम्पल प्रिपरेशन पण खूप महत्वाचं ठरतं वेन यू आर कन्सिडरिंग एनी मायक्रोस्कोपी, बी इट एससीएम or TM. But in ACM, what we generally do is, if it is a powder sample, we disperse it in some solvent like acetone or ethanol, which can evaporate very easily. त्याच्यात डिस्पर्स करायचं, अल्ट्रासोनिकेट करायचं थोडा वेळ, and then a drop of that is put on the conducting substrate. It can be either carbon tape or it can be a sorry, it can be an aluminum sheet. We put drop cast on the that solution onto that tape, and then we dry it. Then we do this kind of coating, sputter coating, if the sample is not conducting, if the sample is non-metallic, and then we use it for analysis. एक 2 मिनिटाचा ब्रेक घेऊया. आय नीड सम वॉटर, देन विल कंटिन्यू. एनी डाऊट्स? कुणाला काही प्रश्न आहेत का? Now we'll continue with another technique called transmission electron microscopy. माझा आवाज ऐकू येतोय ना सगळ्यांना?
Yes, sir.
Okay. So TM basically is an electron microscope that again uses electromagnetic lenses to focus and direct an electron beam, and the data is collected from the beam after it passes through the sample. So that is very important. ACM मध्ये काय होतं की electron beam falls on the sample and then it gets reflected, and then the reflected or backscattered electrons are captured. Okay. In TM, the electron beam has to pass through the sample. That's why in TM, the sample has to be very thin. If it is not very thin, खूप thick sample असेल, the electron beam will not be able to pass through the sample, and then you will not get the information that you need. You will get only one black spot in your image. So that for that you need very thin nanoparticle sample in TEM. Okay. So what kind of information you get? You get full morphological information like grain size, grain boundaries, interface, secondary phases, distribution, defects. Then crystallographic information means atomic structure, macroanalytical information like chemical composition, bonding, electronic structure, coordination number, लॅटिस स्पेसिंग जे XRD मध्ये तुम्हाला जे पिक्स मिळतात ना HKL प्लेन्स मिळतात तसे त्याच्यासाठी तुम्ही डी व्हॅल्यू कॅल्क्युलेट करता सो दोज काइंड ऑफ डी व्हॅल्यूज कॅन बी ऑप्टेन हिअर डायरेक्टली and then you can accordingly by matching with the JCPD's D values you can assign the planes to the those lattice planes. Okay, so that is the beauty of TEM. You can go even up to atomic scale resolution TEM. So what a TM can do, it can do imaging. It can be imaging and direct imaging as well as the phase contrast imaging. Again, phase contrast imaging will depend on the atomic number of the sample. Okay. Then diffraction. So जी information तुम्हाला X-ray diffraction मध्ये मिळते, similar information तुम्हाला इथे पण मिळते. Now you can correlate your X-ray diffraction data with this electron diffraction data, and then you can get even better information about your sample. Okay. Then there are other informations that are obtained like conversion electron beam electron diffraction is data is there, chemical analysis there, like EDS is there, energy dispersive spectroscopy जे आपण ACM मध्ये पण बघितलं. Similar information is obtained in TM also. Then there is another technique called as electron energy loss spectroscopy (EELS). This spectroscopy gives an information like XPS, X-ray photoelectron spectroscopy मध्ये ज्या प्रकारची बाइंडिंग एनर्जीची इन्फॉर्मेशन मिळते त्या प्रकारची इन्फॉर्मेशन आपल्याला इथे मिळते. Energy filtered imaging also can be done. Okay. But we'll focus for this lecture, we'll focus on imaging in TEM, diffraction in TEM, and energy resources spectroscopy in TEM because that is more commonly used information. Other informations are not very common, so I'll not go into the details of that. So these are the basic features of a modern TEM, transmission electron microscope. This is the column. So at the top of the column, there is an electron gun from which the electron beam is generated. Okay. Then there is a lens system in between. Lens system, as I told you, they are basically electromagnetic lenses, condenser lens, objective lens. Then there is a sample holder also, specimen holder in between. And here you get the image, magnified image. Okay. So this is basically the viewing chamber where you get the image. Nowadays, this viewing chamber is directly attached to the computer. So you don't have to see through that viewing chamber. You can directly obtain the image on the computer. Previously, there was this viewing chamber and operators used to view through that chamber, focus and defocus the imaging. So that was a very cumbersome job. But nowadays, because of this technology advancements, you get the information directly on the computer. For EELS, electron energy loss spectroscopy, there is another detector at the bottom. You can see here. Okay, and then that is useful for further. There are different apertures. Apertures basically will determine the thickness of the beam that is interacting with the sample. Based on what kind of information you need, you can vary the thickness of the beam also. Okay. Then there is a EDS detector. Okay, and specimen holder. So obtaining an image in TEM is like watching a movie in the theater, especially the older theaters. जुन्या theater मध्ये काय व्हायचं ते रील नसायचं. तुम्हाला माहिती असेल रीलचे डब्बे यायचे पूर्वी, बॉक्सेस यायचे, आणि तो रील खूप फास्ट स्पीडमध्ये प्ले केला जायचा. ओके, सो हा तो रील इथनं प्ले व्हायचा. देर इज अ लॅम्प, लाईट सोर्स, कंडेन्सर लेन्स इज देअर, रील इज रनिंग. ओके, अँड ऑब्जेक्टिव्ह लेन्स इज देअर. ऑब्जेक्टिव्ह लेन्सचा जॉब काय आहे? फोकसिंग आणि डिफोकसिंग ऑफ द बीम. सो वेन द बीम इज गेटिंग डिफोकस्ड, इट इज प्रोजेक्टेड ऑन द स्क्रीन, आणि तुम्हाला एक मॅग्निफाईड मूव्ही बघायला मिळायची. ओके, सो ही रील रन होत राहायची इथे. टेम मध्ये पण सिमिलर आहे. देर इज अन इलेक्ट्रॉन सोर्स लाईक अ लाईट सोर्स, कंडेन्सर लेन्स, युअर स्पेसिमन, युअर सॅम्पल इज देअर लाईक अ स्लाइड, ज्याच्यावर ते रील तो रन व्हायची ती. ऑब्जेक्टिव्ह लेन्स इज देअर, फ्लोरोसंट स्क्रीन इज देअर ॲट द एंड, and you get a magnified image here. So it's like a watching a movie. So imaging modes are there. So these are three important imaging modes in TM: bright field imaging, dark field imaging, and high resolution imaging. Okay. काय काय डिफरन्स आहे आपण एक एक बघूया. बेसिकली हाय रेझोल्युशन इमेजिंग इज अन एक्सटेन्शन ऑफ दिस ब्राईट फील्ड इमेजिंग. त्याला हाय रेझोल्युशन इमेजिंग याच्यासाठी म्हणतात की यू गेट व्हेरी गुड इमेजेस विथ लॅटिस स्पेसिंग. म्हणजे तुम्ही अगदी ॲटॉमिक रेझोल्युशनच्या जवळ जाता. दॅट इज वाय इट इज कॉल्ड एज अ हाय रेझोल्युशन इमेजिंग मोड. त्यासाठी तुम्हाला थोडेफार ऍडजस्टमेंट्स करावे लागतात. दॅट्स वाय इट इज कन्सिडर्ड ॲज अ सेपरेट मोड ऑफ इमेजिंग. सो विल गो वन बाय वन. Most common mode used in TM for analysis is this bright field imaging. Like in SEM, it is secondary electron mode imaging. Okay. Dark field imaging is analogous to the backscattered electron mode imaging in SEM. Okay. So we'll go through them one by one. I already have told you, ILS detector is there at the bottom, and then there are certain detectors here. So this is the optics of the TM. Electron source, condenser lens, I already told you. Objective lens is there. Then these apertures are there, which will determine the thickness of the beam. Some intermediate, that doesn't mean that there is only one objective lens in TM. There are many lens systems. Some intermediate lenses are also there for further improving the magnifications. Projection lens is there. And then there are two modes of imaging. One is microscopy mode, where you get an image like this, fully focused, fully defocused image is obtained. In diffraction mode, instead of this kind of fully focused image, you will get little bit defocused, little bit focused image, and you will get some spots, bright spots. Instead of an image, you will get some spots. Now, those spots also carry information about the sample. Okay. So, this kind of imaging is obtained. So, when the electron beam falls on the sample and you obtain the image at certain location, you will get this kind of image of the sample. But if you capture the image intermediate, at the intermediate location, you will get the diffraction information, and you will get this kind of diffraction spots. I'll explain later, then you will get the idea. That means when you are getting interrupting this electron beam intermediately, you are getting this kind of diffraction imaging. When you are not interrupting the beam and you are obtaining the image, this kind of imaging mode is there. But in ACM, I told you, you get atomic number contrast in backscatter electron imaging. Okay. But in TEM, along with that, you get more contrast features. One contrast can be because of the thickness. One can be composition, similar to the DSC mode in ACM. So compositional means atomic number contrast is there, but along with that, there is a thickness contrast also. There can be different diffraction or orientation contrast. If your sample has got some strain, some stress in the sample, that also generates this contrast. So you have to be very careful while analyzing the TM data as compared to the ACM data. This TM data contains more information, so you have to be very careful while analyzing the more data in TM. This is one typical example of a TM image. Now here dark region is there, here some bright region is there. You may feel that this is because of the atomic contrast, atomic number contrast or composition contrast, but this may not be the case. This can also be because of the thickness. Thickness of the sample in this region may be small, it may be thicker here. So what is happening is electron beam is penetrating more here, generating more signal in this region. Beam is not able to penetrate more in this region because of the thickness. You are not getting good signal. So that is why you are getting this contrast. That also may be a possibility. So you have to be careful while doing the TM analysis of your samples. Now we'll move towards the modes of analysis of TM. As I told you, there are two modes, bright field and dark field. Field means background. In bright field imaging, the background is bright and your sample looks darker. So that is the ultimate test. In dark field imaging, the background is dark, the sample is brighter. Okay, so based on that, you will understand what is the difference. Most of the TM imaging is done in this bright field imaging. Okay, only whenever you have some, as I told you, atomic contrast or contain your sample contains some materials which have got different atomic numbers, number elements. Like suppose your sample contains cadmium sulfide also, and it also contains some lead. Okay, in that case, you have to do this kind of bright field imaging. Sorry, dark field imaging. Hmm? Or if your sample is, say, some metal in some polymer, and you want to know the distribution of metal in that polymer, then dark field imaging is good. In all other cases, bright field imaging is sufficient. Okay. So remember, bright field imaging, background is bright, sample is dark. Dark field imaging, background is dark, sample is bright. Not only that, the way you capture the signal is also important. In bright field imaging, directly transmitted electron is used in the analysis. In dark field imaging, the directly transmitted electron beam is uh, it is blocked. You can see it is blocked here, and only a little bit say deflected beam. Now this beam is getting deflected again because high atomic number element will deflect more, low atomic number element will deflect it less. So more deflection means more contrast. Less deflection means less contrast. So it is capturing a deflected beam. There is an objective aperture for that. Okay. So imaging mode is different. I'll give you some examples that will clarify the things. This is one sample. Now this sample is like a honeycomb. मधमाशीचं छत्त असतं ना, असं पोळं असतं ना, तसं हे सॅम्पल आहे. आणि त्याचे जे वॉल्स आहेत त्याच्यावर ते सॅम्पल आहे. हे बेसिकली इट इज सम काइंड ऑफ अ पॉलिमर विथ सम नॅनो पार्टिकल्स एम्बेडेड. सो तो जो पॉलिमर आहे त्याचं स्ट्रक्चर जे आहे ते असं हनीकोम लाईक आहे. बाकीचं हॉलो आहे मधलं, फक्त ह्या इथे सॅम्पल आहे एजेसला. अँड इट इज एम्बेडेड इन द पॉलिमर. दिस इज ब्राईट फील्ड इमेजिंग. नाव हिअर द पार्टिकल्स आर व्हेरी शार्प. तुम्ही त्याची इव्हन पार्टिकल साईज मोजू शकता, इतके ते शार्प पार्टिकल्स तुम्हाला दिसतात त्याच्यामध्ये, त्या मॅट्रिक्समध्ये, पॉलिमर मॅट्रिक्समध्ये. But if I want to know the distribution, dark field imaging is better. Here I am getting that contrast, atomic contrast, and I am getting bright nanoparticles embedded into that polymer matrix. Polymer matrix असल्यामुळे त्याचा contrast जो आहे तो तेवढा छान नाहीये. So because of that, I am clearly seeing the polymer matrix here and the nanoparticles embedded into the polymer matrix. So this is the dark field imaging and this is the bright field imaging. I hope now it is clear to you. Second mode of imaging is diffraction. So various diffraction patterns can be generated, like Kikuchi patterns are generated, convergent beam electron diffraction patterns are generated, ring patterns are generated, spot patterns are generated. First two patterns are generated generally in metallurgical samples. Okay. Last two patterns are generated in nanoparticles. I'll show the patterns, then it will be clear to you. Also, those patterns, electron diffraction patterns, can be correlated to the X-ray diffraction. I'll show here. So this is a typical electron diffraction pattern. You can see some rings. तुम्हाला काही रिंग दिसत आहे तिथे. ओके. आणि एक्सरे डिफ्रॅक्शन मध्ये काय दिसतं तुम्हाला? तुम्हाला असे पिक्स दिसतात. ओके. ऍट पर्टिक्युलर 2 थीटा व्हॅल्यूज. आणि या रिंग्स पण पर्टिक्युलर लोकेशन्सलाच आहेत. Now each ring corresponds to one HKL plane. Okay, one ring, one HKL plane. Second ring, second HKL plane. Third ring, third HKL plane or third peak. Okay, so this is how you can correlate. Now here, by knowing the distance of this central spot and the distance of this first ring, means by knowing the radius of the ring, first ring, second ring, third ring, you can calculate the D values here, the HKL plane values, and then from X-ray diffraction data also you can generate the DHKL value for this peak, and so on. And then you can correlate these D values and you can assign the planes, HKL planes. Okay. So X-ray diffraction basically is from the small wavelength. Powder X-ray diffraction is from larger wavelength. X-ray diffraction wavelength generally is 1.54 angstrom. Okay, electron diffraction wavelength we have seen already 0.0008 nanometer. So it is smaller than this. So because of that, you are getting more number of rings here as compared to the less number of peaks here. ओके, कारण की याचा रेझोल्युशन अजून चांगला आहे ऍज कम्पेअर टू एक्स डिफ्रॅक्शन. त्याच्यामुळे तुम्हाला इथे 1 2 3 4 5 पिक्स मिळत आहेत. सो इथे तुम्हाला 5 रिंग दिसायला पाहिजे होत्या, पण तुम्हाला किती दिसतात? 1 2 3 4 5 6 7 8 9 किंवा अजून जास्त आहेत. का दिसत आहेत? बिकॉज ऑफ द स्मॉलर वेवलेंथ. ओके. And electron diffraction is very sensitive to the changes in the crystal structure. So it is a localized technique. X-ray is a bulk technique. तुम्ही अख्ख्या पावडरचा एक्सरे करता. जेव्हा तुम्ही इलेक्ट्रॉन डिफ्रॅक्शन घेता ना, तुम्ही अगदी एक नॅनोमीटर, 2 नॅनोमीटर, 5 नॅनोमीटर, 10 नॅनोमीटर पार्टिकलचा डिफ्रॅक्शन घेता. सो इट मे नॉट रिप्रेझेंट द एंटायर पावडर. एक्सरे डिफ्रॅक्शन मध्ये मात्र तसं नसतं. इट रिप्रेझेंट द इन्फॉर्मेशन ऑफ द एंटायर पावडर. ओके. आता जे मी तुम्हाला इथे सांगितलं, एक्सरे डिफ्रॅक्शन मध्ये तुम्हाला रिंग पॅटर्न मिळतात आणि स्पॉट पॅटर्न मिळतात. रिंग पॅटर्नचा हा एक्झाम्पल मी तुम्हाला इथे ऑलरेडी दाखवलं. दिस इज अ रिंग पॅटर्न काइंड ऑफ अ स्ट्रक्चर. रिंग पॅटर्न कधी मिळतात? व्हेन युअर सॅम्पल इज पॉलिक्रिस्टलाइन. म्हणजे पॉलिक्रिस्टलाइन मध्ये काय असतं? डिफरंट ग्रेन्स आर ओरिएंटेड इन डिफरंट डायरेक्शन्स. बट व्हेन युअर सॅम्पल इज सिंगल क्रिस्टलाइन मध्ये कसं असतं? डिफरंट ग्रेन्स और डिफरंट HKL प्लेन्स. देर आर नो डिफरंट HKL प्लेन्स. HKL planes are oriented in particular direction, in one direction. Then it is called as a single crystalline material. So single crystalline material असेल तर तुम्हाला स्पॉट लाईक पॅटर्न मिळतो. रांगोळीचा जसं तुम्ही ठिपके काढता ना, तशा प्रकारचे स्पॉट लाईक पॅटर्न तुम्हाला मिळतो. And when your sample is polycrystalline, you get ring like pattern like this. I'll show some examples so it will be clear to you. So this is a spot like pattern in a single crystal. Okay. Now if I am ऍडिंग दोज सिंगल क्रिस्टल टुगेदर, जर खूप सारे सिंगल क्रिस्टल मी एकत्र केले तर मला पॉलिक्रिस्टल मिळेल वेगवेगळ्या ओरिएंटेशनचा. त्याच्यामुळे काय होईल की हे स्पॉट लाईक पॅटर्न एकमेकांच्या खूप जवळ यायला लागतील आणि असा रिंग लाईक पॅटर्न तयार करतील. गॉट इट? सो सिंगल क्रिस्टल असेल तर स्पॉट लाईक मिळतो, पण व्हेन सेम मटेरियल इज पॉलिक्रिस्टलाइन यू विल गेट रिंग लाईक पॅटर्न लाईक दिस. ठीक आहे. दिस इज वन एक्झाम्पल. This is small. These are different crystals. One crystal, second crystal, third crystal, fourth crystal, fifth crystal. Grains basically, not crystallites. Okay, but their numbers are limited, so you are getting a spot pattern like these. Okay, but when there are so many number of crystallites, large number of crystallites coming together, and you are taking the electron diffraction, you will get ring-like pattern like this. Okay. So these are the ring-like patterns. हे अशा प्रकारचे ring-like pattern मिळतात whenever you are getting a polycrystalline sample. This is the ring-like pattern of a polycrystalline gold. आता तुम्हाला इथे हे काही नंबर्स दिलेले आहेत, तुम्हाला दिसत नाहीये थोडे विजिबिलिटी मध्ये. बट these are basically the HKL planes for that particular ring. ही एक रिंग आहे, इथे एक रिंग आहे, इथे एक रिंग आहे, इथे 2 रिंग्स आहेत म्हणून 2 HKL प्लेन्स आहे, इथे 4 रिंग आहे म्हणून 4 HKL प्लेन्स आहे. This is for gold sample. But if you look at X-ray diffraction of gold, you will get at least 3 to 4 peaks only, not more than that. But here you are getting more peaks. This is spot like patterns, म्हणजे रांगोळीच्या टिपक्यांसारखे तुम्हाला पॅटर्न मिळतात. So this is single crystalline sample. This is convergent beam electron diffraction pattern. This is, as I told you, for metallurgical sample. This is a stainless steel sample, single crystal, but it is cut and it is viewed along a particular direction. It is viewed along a 111 zone axis. That is why you are getting a complex structure like this. हे खूप महत्वाचं असतं मेटलर्जीमध्ये. तुम्ही जेव्हा स्टीलचे वेगवेगळ्या फेजेस बघता, SS3146 झालं, 304 आहे, देर आर मेनी अदर्स ऑल्सो. How do we differentiate them? They are differentiated using this kind of diffraction pattern. This kind of pattern for 316 steel, 316 grade steel will be different. 304 grade steel it will be different. अशा प्रकारच्या काही लाईन्स पण मिळतात, केकूची लाईन्स म्हणतात त्यांना. हे दे अगेन रिप्रेझेंट ओरिएंटेशन्स, डिफरंट ओरिएंटेशन्स अलॉंग डिफरंट ग्रेन्स. पण हे पण मेटलर्जी मध्ये वापरतात, सो विल नॉट गो इन टू द डिटेल्स ऑफ दॅट. In short, the crux of matter is whenever your sample is single crystalline, you are getting spot-like patterns. This is again an example. This is the single crystal of Fe, iron. It is in the BCC phase, crystalline phase, body center cubic. It is a thin film with 001 orientation. And if you look at the HKL planes, this spot corresponds to 110 plane, this spot corresponds to 020 plane, this corresponds to 200 प्लेन. हे कशावरनं काढले तर या सेंट्रल स्पॉट्स पासून यांचं डिस्टन्स काढलं, त्याच्या डी व्हॅल्यूज काढल्या आणि त्या पर्टिक्युलर प्लेनला मॅच केल्या. ओके, दिस इज पॉलिक्रिस्टलाइन सॅम्पल. दिस इज PD2SI, पॅलेडियम सिलिसाइड आहे हे. सो बाय नोईंग द रिंग्स वी कॅन फाइंड आउट द फेजेस अँड HKL प्लेन्स ऑफ दॅट सॅम्पल. नाउ आपण सिंगल क्रिस्टलाइन बघितलं, पॉलिक्रिस्टलाइन बघितलं. इफ माय सॅम्पल इज अमॉर्फस, देन हाऊ विल आय गेट द diffraction pattern? In amorphous sample, you will get a hollow ring like this. एक प्रकारची एक hollow ring मिळते तुम्हाला, जी खूप थिक आहे. इथे तुम्ही जर बघितलं, या रिंग खूप शार्प आहेत, बट ही रिंग जी आहे ना, ही हॉलो आहे आणि थिक आहे. सेम सॅम्पल, इफ इट इज पॉलिक्रिस्टलाइन, you are getting rings. Same sample, if it is amorphous, you are getting a hollow, diffuse, thick, hollow ring. Okay. These are some examples, typical examples. This is an example of nanoparticles. This scale, if you look at, it is 200 nanometer. That means the distance between this point to this point in the scale is 200 nanometer. Now, by knowing this scale, you can calculate the particle size. Particles are very small, maybe around 40 to 50 nanometer. Now, we magnified this. Again, magnified this. Now, at this magnification, the scale is 20 nanometer. That means this distance is 20 nanometer. So this particle may be around 30 nanometer. This may be around 40 nanometer. This particle may be around 5 to 10 nanometer, 5 to 7 nanometer. Maybe this particle is 10 nanometer in size. By knowing this size, I am approximately telling. But if you want to measure it properly, you can take one line in your PowerPoint presentation. Keep this image in the PowerPoint presentation. Take one line, match this line with that line. Now you know the distance of length of that line in PPT, and now you can attach the line to every particle, and from that you can calculate the approximate size. But there are some softwares also which can do this job. So in TM image, you get the information about the particle size and shape, and also about the crystalline nature. This is the electron diffraction. This is ring-like structure. Okay, that means it is a polycrystalline sample. This is another example. This is example of a single crystalline sample. This is a rod-like structure. Scale is 200 nanometer. That means these rods are, if you look at this thickness, rod is around 200 nanometer thickness. This rod, this may be around 80 nanometer. Some of them may be even smaller. But length is more. Length may be around 1 to 2 micron. Okay. Now I further magnified. This scale is 220 nanometer. Now I magnified this region. Then I got one more region of one rod of say 50 nanometer thickness. So I magnified this region. This is here. Here you can see some lines. These lines basically are lattice spacings. Okay. Now the distance between two lines is 0.387 nanometer. When I matched it with the particular element, particular material, the plane is H001 plane. I further magnified this region. Now I am getting the distance 001 plane, and I can find out the D values. And when I take the electron diffraction pattern of this region, I am getting single crystalline spot like region. Okay. And these spots corresponds to different planes like 001, 101, 111, and so on. Okay. So this kind of information can be obtained using TEM imaging. This is another example. This is the example of CDS nanoparticles. Excuse me. These are irregular shaped nanoparticles. Scale is 50 nanometer, 20 nanometer, and 5 nanometer. Okay. And now I have taken the electron diffraction in this region. I'm getting spots, and those spots are basically hexagonally arranged because this metal basically is hexagonal. Okay. So I'm getting the information about the particle size and shape from these two images. I'm getting some lattice spacing image from here. But the image is not very clear. I'll make it clear in the next slide. Scale is 5 nanometer. Can you see the lines now clearly? Lines are oriented in one particular direction. These are basically the lattice planes. Okay, and I can calculate the lattice spacing this between these two any two lines, and then I can assign it to a HKL plane. But since these lines are oriented in particular direction, that means that this material is single crystalline. How do I confirm this? I confirm this by using this SAED pattern. Here I can see the spots. The spots can tell that that material is single crystalline. This is another example. Again, some flower-like structure. I can calculate the thickness of the length of the petal of that flower, thickness of the petal of that flower. I can also calculate the lattice spacing, see whether it is single crystalline or polycrystalline. Now this sample is polycrystalline because in this region the grain is oriented in this direction, but here the grain is oriented in another direction. Adjacent to that, the grain is oriented in third direction, and accordingly, I am getting the ring-like structure. So polycrystalline sample is there. This is another example of a polycrystalline sample. This is one more example of a polycrystalline sample. So this is how I can do the TM analysis of various samples. Now, till now I have done the only the imaging. I can do the EDS also. So this is the example of a copper dope CDS nanoparticle. Flower-like structure is there. I can do the lattice spacing studies also. Now because I have dope CDS, lattice are not straight. सरळ नाही आहे. तुम्ही इथं जर बघितलं ना तर इथे थोडे सरळ आहेत, इथे थोडेसे ते बेंड झालेत. कारण की त्याच्यात डिफेक्ट्स तयार झालेत बिकॉज ऑफ द सीडी डोपिंग सॉरी कॉपर डोपिंग. कॉपर डोपिंग मध्ये त्या सीडीएसच्या लॅटिस मध्ये थोडे डिफेक्ट्स तयार झालेत. ओके. सेकंडली आय वॉन्ट टू know the presence of CD and its distribution because I have done the doping. So I should know whether it is doped uniformly on the sample or it is doped in a particular region. So I had done EDS first. I found out the presence of copper. Okay. So I am getting the peaks of copper, sulfur, CD. Okay. So I found the presence of copper here. And then I wanted to know the distribution. So I had done the mapping. Like I had done the map, I can do the mapping in SEM mode. I can do the elemental mapping and EDS in TM mode also. So in TM mode, when I have done the mapping, I can see the presence of CD. I can see the presence of sulfur on those particles. These two particles I have chosen for the mapping. So I can see the presence of CD. I can see the presence of sulfur, and in the same region, I am seeing the presence of copper. That means copper is uniformly doped in the sample. Okay. This is one more example. This is basically a composite of CDS and ZNO. Nanocomposite is there. Some sheet-like structure is there and some particles are also there. You can see some particles here, here, and also on the sheet. And then there is a sheet-like structure which is covered by particles in some spaces and it is empty at some spaces. So I wanted to know which one is CDS, which one is ZNO. So I have got different ways available. One of them is find. I know the lattice spacing values, DHKL values of CDS. I know the DHKL values of ZNO. Okay. So what I will do is I'll do the high magnification imaging, high resolution imaging of these samples for the sheet region and for the particle region. And then I'll find out the D values for the particle region and for the sheet region and match with HKL values of CDS and ZNO. So I did that. I found out that the sheet-like region is ZNO, particle-like region is CDS. But I wanted to further confirm. How will I do that? I'll use EDS analysis. So what I did was, I did EDS in the particulate region, spectrum 1. I did the EDS in the sheet-like region, spectrum 2. Again, I did the EDS analysis. What I observed was in the particulate region, CD and S are dominating. See, more presence of CD is there, 37%, 34%. CDS is more dominating. Zn is only 8%, O is 19%. Now, when I did the same analysis in the sheet-like region, I am getting more Zn, 24%, more oxygen, and less CD and less S. I am still getting CD and S because CD and S particles are there on the sheet of that on that ZNO sheet. Okay. So this way, I had done another confirmation test of presence of CDO and ZNS, ZNO and CDS. Third confirmation test was this elemental mapping. So I did mapping in the region where particles are also there and sheet is also there. What I observed was in the sheet-like region, I I observed the presence of oxygen and zinc. So this is sheet-like region. More zinc is there, more oxygen is there. In the particulate region, this is the particulate region, the darker one, this one and this one. I am seeing more presence of sulfur here and here, more presence of cadmium here and here. So again, I confirm the presence of composites. Okay, so this is the beauty of SEM and TM analysis, which is not present in many other analysis techniques. Okay, so like SEM, in TM also sample preparation is very important. So in TM, if you have got a powder sample, sample analysis is done by dispersing that powder in some solvent. The most suitable solvent again is acetone or IPA or ethanol. We use that because they can evaporate very fast. So what we do is we disperse that powder in ethanol solvent, ultrasonicate for some time so that the particles are deagglomerated, they are broken. Then a drop of that is drop cast on a copper grid, polymer coated copper grid or carbon coated copper grid. It is like this. And that grid diameter is only 3 mm. 3 mm ची ग्रीड असते छोटीशी त्याच्यावरती आम्ही फक्त एक ड्रॉप कास्ट करतो आणि त्या ग्रीड वरती असं एक कार्बन आणि फॉर्मरची फिल्म असते ज्याने त्याला एक रिजिड सरफेस मिळतो आणि कॉपर थ्रू तो जो कंडक्टिंग पाथ पाहिजे असतो ना आपल्याला तो मिळतो त्या त्या ग्रीडला ओके तर ही छोटीशी ग्रीड एका सॅम्पल होल्डरला लोड केली जाते अशा प्रकारचं ते सॅम्पल होल्डर असते इथे ती छोटीशी ग्रीड ठेवली जाते and then that grid is loaded into the machine. So this is a typical TM machine. Then the analysis is done. This is how the sample preparation is done in normal cases. Now, as I told you, you have to combine your analysis. So this is the example of combined analysis of SEM and TM. So this is the SEM analysis of one sample where it is shown to be made up of sphere-like particles. The TM analysis of the same sample is given here. Again, you can see the sphere-like particles. Okay, so this kind of combined analysis is also done a lot of times. Okay, so I'll stop here now. I thank a lot to the principal of LVH College, Nashik, head department of chemistry, all the organizing committee members, especially my friend Tahire sir, and last not the least, to all the participants for your patient listening.
Thank you, sir. Anyone have any question, student, please? Sir, one student is asking a question.
Yeah.
In a chat box.
Yes,
So,
what is the question?
sir, which solvent is suitable for TM?
The most suitable solvent for TM is ethanol. See, the choice of solvent depends on what kind of sample you are having. For most of the samples, ethanol is the most suitable solvent. But if some organic solvent sample is there where it dissolves in ethanol, then in that case you have to choose some other solvent. Or some biological sample is there. In that case also, ethanol can denature that biological sample. In that case, you can use water as the solvent. But the problem with water is it takes a lot of time to evaporate. So what we do in case water is the solvent, what we do is we drop cast on that copper grid and then we keep it overnight so that all the water gets evaporated.
Another question also asked by says, yeah, any external sample is accepted for analysis, sir?
For at CIMET, yeah, we accept external
Ex-
samples.
ex-
We accept external samples for analysis at CIMET, but there are charges for that. The problem is we have to maintain this facility. The cost of the machine is also very high, and maintenance is also very high. We have to pay the AMC of around 12 to 15 lakhs for TM analysis for that TM machine. Apart from that, there are other expenses like operator charges are there. We have to appoint one operator for working on the machine. We have to use some liquid nitrogen for the analysis. So because of all those charges, we have to put some charges for the analysis also. So the charges are roughly around 5,000 rupees plus GST, around 5,900 per sample.
okay, sir. Okay. Uh,
For TEM. For
if
ACM, it
there
is
are no
lesser.
any
For ACM,
further
I think it
questions.
is around 2,000 plus GST.
Okay, thank you, sir. I think there are no any further questions, sir. So we will proceed to the vote of thanks. With the session concluded, I now proceed to the vote of thanks, sir. On behalf of Nite Venkatrav Hire Art, Science and Commerce College, I sincerely thanks Dr. Manish Kumar Desinde, sir, for his excellent presentation and for taking our question. We also thank all participants for attending and engaging.
Sir, sorry, 1 minute.
Special thanks to all.
Sir, sorry, 1 minute. Somebody
Yes,
has
sir.
asked me the question.
Oh,
Sir, in my ACM, there is one peak of gold. I am asking to operator, they give the reason due to coating. Yeah. So if your sample doesn't contain gold, but still gold is present, that is because of the coating. I told you in the sample preparation of ACM, if your sample is not conducting, the operator puts a conducting layer in your on your sample. So that conducting layer can be from gold. Sputtering of gold is done generally as a coating layer, conducting coating layer. So that in your EDS, maybe that gold peak is due to that sputtering. Okay, so you can ask the operator to remove that gold uh, signal. Okay, so if he will remove, you will get only the stoichiometry of your sample. Got it?
thank you, sir. Thank
Yeah,
you.
yeah, yeah, sir. Please, you may continue.
Okay, sir. Thank you, sir. Uh, Also, I will especially thanks to the organizing team. Thank you, sir, and have a good day, sir. Thank you.
Thank you very much. My contact details are with sir. Otherwise, you can email me at this. I think I have stopped sharing. Uh, just a minute. Huh? You can contact me at. Hey, you can contact me on the email address. Yeah. So shall I leave the meeting now? Hello.